presentation. Next, if there is any question, please.
Okay, thank you very much.
Thank you. If not, we go further with Iulia Poenaru. I think it's here.
Good afternoon.
With the paper Microstructure Analyze of Non-Metallic Inclusion in Continuous Cast Steels. Please, Iulia.
I will share my desktop. Please inform me if it can be seen.
Yes, it's okay. We can see your presentation.
So good afternoon. My name is Poenaru Iulia, and under the coordination of Professor Erica Ardelian, I present to you today the paper work Microstructure Analyze of Non-Metallic Inclusions in Continuous Casted Steels. The research presents a part of my PhD thesis regarding analysis of non-metallic inclusions in continuous casted steels, which purpose is to use it in manufacturing hydraulic cylinders in automotive industry. In this phase of the research, 20 charges of steel were analyzed. The steel was manufactured in an EBT LFVDTC continuous casted furnace. Further is presented the microstructure analyze for simplify one sample. From microstructure analyze are identified steel retraction 4th grade. You can see it first in the center. Central segregation represented by the concentric dark spots and here. And the major defect is the marginal cracking that leads to semi-analyze. The microstructure analysis detects an isolated inclusion with irregular shape and exogenous provenience. The spectrometer is highlighting the peak of each element localized in defected area so that nature inclusions to be identified. Element map analysis is showing the chemical distribution of most important elements in designated area. From previous analysis, mangan and calcium composition stood in evidence, and by comparing these two elements composition in the final sample and directly in the detected inclusions is observed a low mangan concentration and an excess of calcium in inclusion area, which is leading to conclusion that the defect is a calcium oxide. The cause of appearance is due to refractory wall peel of the casting ladle. In conclusion, semi-analyze provides valuable information about the nature of the inclusion and therefore to be able to identify the root cause of defect formation, and so to be able in the future to think, to find preventing actions. Thank you for your attention. If there are any questions, I am standing to your disposition.
Questions, please.
Okay, thank you very much, Iulia.
Thank you.
Okay, our next speaker then is Adriana Bobora. Possibilities of recycling of sideritic tailings in steel industry.
Good afternoon. My name is Bobora Diana Lăcrămioara, and I am his PhD student of engineering faculty of Hunedoara. And I want to present the research's possibilities of recycling of sideritic tailings in steel industry. In the context of the circular economy, the production of steel in the electric arc furnaces is very well integrated. the promotion of recycling technologies that lead to improve the product quality, and the expansion of the raw and auxiliary material by facilities the closure of the recycling loop, the processing of powdered waste in the set of technological operations through which they are processes or for their use under the conditions required by the beneficiaries. The paper presents a technological solution for viling the sideritic tilings and the ferroslates in the form of carbofer byproduct usable in the steel industry when foaming slag in the electric arc furnace. Laboratory tests were carried out at the Faculty of Engineering Hunedoara using sterile sideritic recipes and iron steel sludge. In Hunedoara's area, following the preparation of the sideritic or use in the processing of the agglomerate, they are three tilings ponds with sideritic waste at Taliuc. The characteristics of the tilings are given by the ore from which it comes in the furnaces of the milling determined by the preparation process. Sometimes it is possible that some characteristics of the tilings are worsened by the additions in the preparation process. For the determination of the quantities of waste deposited in ponds, topographic measurements were made under a research contract. The measurements were made at the tiling ponds number 1, 2, and 3 from Taliuc mining. The areas occupied by the sideritic waste and are 25, 18, and 32 hectares, respectively. The quantities deposited amounted to about 20 million tons. The ponds are in the processing of greening. The deposited sideritic waste, due to the elements in the chemical composition, has a potential for exploitation and must be found economically efficient processing technologies and beneficiaries of the resulting byproducts. The work focuses of identifying solution for processing the sideritic waste and obtaining various byproducts usable in the industry, especially in the steel industry, and auxiliary material for the elaboration of steel. A processing solution is to obtain a carbofer product, mechanical measure. The carbofer process is a technology that allows obtaining a mechanical mixture obtained from pulverulent waste containing iron and carbon, which can be used in the production of cast iron or steel. The economic advantage lies in the immediate transfer of cost for the storage of waste to other destinations. The paper presents the experimental research carried out in the laboratory phase on the possibility of using sideritic sterling mixed with ferroslurry, resulting for the steel industry in order to obtain the carbofer byproduct usable in the elaboration of steel as an agent for foaming slag. A number of 5 recipes for obtaining the carbofer byproduct have been experienced. In their composition, the following weights were used: sideritic waste, ballast furnace, ferroslurry, ground slurry, electro scrap, and lime powder. In this is chemical composition present. In Through this scheme, we present the technological flow for obtaining the carbon byproduct, siderite waste, ferrous sludge, thunder sludge, agglomeration partner sludge, electrode residues, lime dust. Through volumetric sieving, obtain the granulometric fraction over 3 millimeters granulometric fraction, it grading, dosing, homogenizing, and it is obtained carbon byproduct. Here are some images from the research carbon type by product. Conclusions, the processes materials contain the elements iron, carbon, calcium, useful to the process that take place in steel aggregates. They share in obtain product falling within the limits. Iron between 15 and 36%, calcium between 12 and 11%, carbon between 15 and 25%. In steel making aggregates to use for the carbon byproduct with high carbon and iron content ensures a good dissolution of iron oxide in slag in very short time, and also very quickly set the slag balanced metal bath which ensures good oxidation of carbon in the bedroom and an intense foaming of slag. So ensure the work with the arc covered. The product of foaming must be obtained after experimental recipes can be used in the best conditions for foaming slag, providing an appropriate composition for this when developing steel in electric arc furnaces. Thank you for your attention.
Thank you very much, Adriana.
Thank you very much.
If there is any questions, thank you for your nice presentation. If there are not questions, we will go to the next speaker, which is Belma Islamovic. With,
I'm here.
Yes, hello. With the paper tests and analysis of the results of the mechanical properties of various aluminum alloys. Please.
Hello, everyone. Thank you. Hello, everyone. My name is Belma Islamovic, and I'm a master's student at the Technical Faculty of Bihać, University of Bihać. Today, I'm going to talk about tests and analysis of the results of the mechanical properties of various aluminum alloys. This paper will explain the procedure for conducting tensile tests and will identify the various properties of the tested aluminum alloys using standard test tubes. The purpose of the experiment is to verify if the properties of the tested materials align with the specifications provided by the supplier. The results are crucial for determining the construction's durability and suitability for its intended use. The test was conducted using test tubes prescribed by the EN 10002 standard made of 3 different aluminum alloys, aluminum with magnesium, with silicon, and with copper. 4 tubes of each material were used. You can see the table 1 with physical and mechanical properties of those 3 aluminum alloys, and also the figure 1, which shows dimensions of test tubes for tensile testing according to the standard. Next slide shows figure 2 with prepared test tubes for tensile testing. The tensile tests for the test tubes were conducted using the Shimatsu brand tensile testing machine with a 50 kilonewtons capacity, following the EN ISO 6892-1 standards the test was carried out at room temperature without any prior heating or cooling of the test tubes. The test tubes were clamped in the jaws of the machine and as illustrated in the figure 3. The material of the test tube experienced a tensile stress leading to structural changes that affected its original characteristics. In all cases, the neck of the test tube cracked due to its smaller dimensions and the high stress concentration. The outcome of the test is illustrated in a force elongation diagram. First one is for aluminum alloy with magnesium. Second one is with silicon, and third with copper, and there is a huge difference between them. The detailed values of individual mechanical properties are displayed in table 2. The results of the tensile test demonstrate the importance of selecting the right material for building structures in use and how the lifespan of these structures depends on that choice. The material chosen depends on the purpose and expected stresses. The analysis of the experiment results leading to the following conclusions. Adding silicon and copper alloying elements to aluminum increases the material's elastic area. There is a significant difference in the strength of aluminum alloys. For instance, the alloy with aluminum with magnesium has the weakest properties with the lowest tensile strength of up to 12 kilonewtons. On the other hand, the alloy of aluminum with copper has the greatest influence on improving the material's properties with a maximum force of 27 kilonewtons. And copper as an alloying element results in the toughest material with a maximum elongation of almost 16 millimeters, while magnesium and silicon have nearly the same ductility, around 13 millimeters. The chemical composition and the participation of alloying elements within an alloy significantly change the base material's composition and affect its mechanical properties. This helps achieve the necessary characteristics for special purposes and expand the material's range of use in practice. Thank you for your attention.